Okay, ninth graders, today we are going to talk about magnetism. And it's kind of hard to define magnetism without using the word magnet, but I think all of you have experienced at some point in your life the way magnets interact with one another. And the behavior of magnets when they are near each other is known as magnetism. And so that's the interactions and forces between magnets. Now, right here, you see a picture of a bar magnet. You're probably used to refrigerator magnets, and those are a little bit different, but a bar magnet is basically just a piece of metal, and it's got two ends to it. You've got the N end, which stands for north, and the S end, which stands for south. And all these kind of spider lines around it, those are lines that are indicating the magnetic field. And so that's where the strength of the magnet is the most, where those lines are closer together. So at the ends, which we call poles, you have your strongest magnetic field. Now, magnets behave similarly to charges, the poles do. So like poles repel each other, north repels north, south repels south, and opposite poles attract. Now, those field lines that I was talking about before, they have a direction to them, and they go from the north end of a magnet around to the south. So normally what we would do is we would do a lab where we take iron filings and sprinkle them around a magnet, and you would actually see this pattern form. Obviously, we can't do that with where we're at, but I'm going to have you do a simulated lab activity that will have a whole bunch of little tiny compasses in the background, and they're all going to point in the direction of the magnetic field wherever you are. Not everything is magnetic. Only some metals are magnetic. Iron, cobalt, and nickel are some of the magnetic metals. Things like aluminum, copper, and some other metals are not magnetic. So if you've ever tried to attach a magnet to a pop can, you notice that it didn't work. Or if you try to use a magnet on money, it does not work. So what's going on inside a magnet? You have these little regions of space that are called domains. And every domain actually acts like its own little magnet. And each of those magnets has a direction associated with it. If you have a metal that is not acting like a magnet, that means that their domains are all pointed in random directions that basically are canceling each other out. If you magnetize a metal, you can get all of those domains to generally line up in one direction, and now you have what's called a magnet. Earth has a magnetic field. You can kind of pretend like there's a big giant bar magnet in the Earth, as shown right here, but that's actually not the case. It's the Earth has a core, and there's an outer part of that inside core that's liquid, and that liquid circulates, and that creates an electric current, which in turn can create a magnetic field. I'm simplifying this, but it acts as if there's a big giant bar magnet in the Earth. Now, the odd thing is that even the place that we call the North Pole is actually where the south magnetic pole of the Earth is. Now, you might say that's kind of weird, because why do we call it the North Pole then? And the reason is our compasses all point to that place, which was called the North Pole long before they figured out how magnets worked. A compass is a small magnet, and the North Pole of that magnet is attracted to the South Pole of the Earth, and that's why it points to what we call the North. It's confusing. Again, here's the geographic South Pole, magnetic North Pole, and vice versa up here. But look at over here, we've got these compasses, and the red tip of that is the North Pole of that compass. The North Pole is going to attract to the South Pole of the Earth. Electromagnets, you can make a magnet by running current through a wire. Currents create magnetic fields. If you make a loop of wire, you still create magnetic fields if you have current running through it. It's just shaped a little bit differently. If you have many loops of wire, you create what's called a solenoid. And that, again, that's an electromagnet, but the strength of the field is on the inside of the coils. And you can make really, really strong magnets doing this. And you can electrify copper and things that are typically not magnetic to create these magnetic fields. And so the whole crux of what we're doing is we're trying to figure out, how do we create electricity? How do we make electric current? And we do that through a process called electromagnetic induction. And we know that if you create a current, that creates a magnetic field. Well, what if you create a magnetic field? Will that create a current? And indeed, that is what will happen. Now, the thing is that you need to change the magnetic field in the loop of wire. So you can't just take a magnet and stick it inside a loop of wire and think, oh, electricity is going, electrons are going to move now. You need to move the magnet back and forth, or you need to turn the magnet. And you're going to see that in the lab simulation that I have you do. So a machine that does that, here's a hand crank generator. There's a magnet inside here. It's got loops of wire around it. If I crank that generator, that will create electric current. That will light up this light bulb. Okay, so basically what we need is big giant machines that can turn magnets inside coils. And so that's what we have at power plants. And we have either steam turning turbines that make this happen. We have falling water in hydroelectric power plants. We have geothermal energy. I mean, most of the time you're just using hot water and steam to turn stuff. But again, you can use windmills to do it. Solar power works a little bit differently, but most of the time you're turning magnets inside a wire, and that is done by a generator to produce electricity. Here, let me play this video.
Here's a question for you. How many people does it take to turn on a light bulb? The answer seems simple. Just walk into a dark room, flip a switch, and instantly you can see, right? Well, the truth is there's a lot more to generating and delivering electrical power than you've probably imagined. Hi, I'm Lee Patrick Sullivan with Energy Now, and this Energy 101 video explains the system used to generate electricity. And it also explains what it really takes to turn on a light bulb. In order to understand energy, we first need to start at the source, literally. Mother Nature provides the natural resource we use to generate power. From natural gas to coal, ocean tides to mountain winds, the energy we need to create electricity must first be mined, harnessed, or collected from the earth. Some of these resources are finite, including fossil fuels like coal and oil, but others are unlimited, like solar or wind power. But a lump of coal or a strong breeze alone won't create the power that turns on your light. For every energy source, a chemical or mechanical process is required to turn it into usable electricity. Every day, researchers work to find innovative ways to use our limited resources, process raw materials, harness renewables more efficiently, and find entirely new energy sources. Today, the majority of America's electricity comes from thermal power plants. Fuels like coal, natural gas, biomass, and uranium are used to heat water until it produces steam, which powers a turbine and generates electricity. That steam turns propeller-like blades around a rotor inside the turbine. This turning rotor connects to a main shaft, which spins magnets with a coil inside a generator. It's the generator inside a turbine that converts mechanical energy into electric energy and creates electricity. Steam is an efficient method of producing electricity because the water can be recycled and reused as it changes back and forth between liquid and gaseous states. Transporting electricity from the power plant to your home is an entirely different process. Current technology cannot cost-effectively store large amounts of electricity, So significant challenges exist when it comes to transferring that electricity across long distances. Just enough electricity has to be generated to meet demand at all times and be transmitted through power lines to reach your light switch. Too much or too little power can crash the transmission system and cause a blackout. That's why a complex mix of logistics, management, and infrastructure is needed to transmit electricity from power generators to consumers. Enter the electricity grid, also known as simply the grid. The North American electricity grid is actually made of 4 large grid systems: the Western grid, the Eastern grid, the Texas grid, and a grid covering the Canadian province of Quebec. These independent regional networks of power plants and transmission lines carry electric energy at high voltage within their area to local utilities. There are very limited links between the 4 grids, which means electricity generated from a wind turbine in West Texas cannot reach an apartment building in New York City. For electricity to move through one of the 4 grids, its voltage must first be increased by a device called a transformer. Then the electricity can travel long distances across high voltage transmission lines. These high voltage lines are generally strung between giant metal towers. They stretch for miles from power plants to local substations in each neighborhood. You've probably seen substations along the side of the road and wonder what they do. Well, their job is stepping down electric voltages from levels as high as 765,000 volts closer to the 110 volts you use in your home. The electricity from the power line on your street passes through another transformer, which steps down the voltage once more, and then it travels along the line into your house. From there, the electricity enters your breaker box, and it is then distributed to light sockets and outlets. All you have to do is flip a switch. So, as you can see, from the raw materials to the power lines on your street, there's so much more to the electricity ecosystem than meets the eye.
All right, so again, here they go. We've talked about energy transformations already, so I'm not going to have us go through that again. But again, here's a picture of what he was just talking about in the video. We actually don't have many coal-fired power plants in Minnesota anymore. The one down at Black Dog just switched over to natural gas about a year ago. But it all, again, is the same. You're heating up water using some kind of fuel, and then that hot water turns into steam, and that turns the fans here in the turbine, which cranks the magnets in the wires, and then that makes the electrons move, and then they shoot through here. Same thing here. Now you've got water in a dam. That water is not being heated up, but as it falls through a height, it turns the fan, and then it flows out. But that turning makes this makes the electrons in those wires again move. In windmills, you get rid of the hot water. You're just using wind to turn the blades. And finally, motors. Motors are basically just the reverse of generators. So generators turn magnets to create electricity. Motors take electricity to turn the shaft. So think of the electric motors that we use all the time in fans, in RC cars, there are little motors that make doors open, like when you go to Target. Any electric motor basically is using electricity to cause magnets to turn, and then those magnets are connected to a shaft, which is connected to a fan blade or a wheel or something that you want to turn. And that finishes the notes for your 9th grade year.